this 31? Yes, Omkar. Am I audible? Hello. Okay. Right, students, we'll start the today's class. Actually, today I have faced some technical difficulty. Actually, my system got crashed in the last moment, and all my data also I'm not able to recover from that system. I'll try to manage today's class actually because that failure, breakdown of my system, all the PPTs, notes, everything is there in that particular system. So whatever the material I have in my mobile now, I'll use that, and with that I will able to take the today's class. Voice is clear, right?
Yes, sir.
Okay, fine. So in the previous class, we have discussed about decoders and encoders. Before we proceed further, are there any difficulties, doubts that you have from the portion which we have covered in the previous classes? Any doubts? If anybody has any doubts, you can ask me. All of you understood decoder fully? Because that is very important part from your examination point of view also. Definitely you can expect the question on decoder, encoder, right, multiplexer. Those are the three important data processing circuits we have studied. All right. How to what is the drawback of normal decoder, right? And sorry, what is the drawback of normal encoder and how that is overcome in the priority encoder? That also we have discussed in the previous class. I hope all of you understood what exactly you mean by priority encoder. Yes? Is that clear? Priority encoder concept?
Yes, sir.
Yes, for others? Rohit?
Yes,
Is
sir.
it clear? Is it clear? You understood the priority encoder concept? Yes?
Sir, I didn't attend previous two
Good,
classes.
very good. Oh, then you have not bothered also to go through the classes, what has happened. In fact, I want to inform all of you here, all the classes which will be taken immediately after the class on the same day, these classes are uploaded on my YouTube channel. If you have missed, you can definitely go to the YouTube channel and you can just have a look at the videos which are uploaded there, right? So you are not bother also to check that, Rohit.
Sir, I'll check.
All the videos are there already. Almost I think around 20 previous 20 classes videos are there in that my personal channel, not on the JCE Connect channel, right? So anybody like who misses the classes, they can go there and you can have look at those classes which are uploaded there. I hope all of you know that YouTube channel address. All of you are having it or no? Yes? Or else just in the YouTube, if you search my name, you will get this. Or those who have not yet visited, I have posted that YouTube link in the chat box. So you can just copy it and keep it somewhere so that whenever you want to refer those lectures which are uploaded there, you can definitely go through this particular link which is shared in the chat box. Okay, so I assume that there are no doubts in the portion which we have covered so far from this module 3, that is multiplexer, decoder, encoder. I'll proceed further, and in today's class we'll discuss one more important circuit or one more important combinational element we can call what is called as a tri-state buffer. So what exactly you mean by that tri-state buffer? That's what we are going to study in today's class. Right? Is the screen visible? Yes? Is the screen visible?
Yes, sir.
Yes, sir.
Okay, of course, as I said, I have lost all my PPT's notes. Maybe definitely I'm going to recover them. So only today's class, the notes of one of your senior students now who are there in 5th semester. I ask her to just take the photo and send me the PDF of this particular like notes which I have given them in the previous year, that is last year, when they were in 3rd semester, right? That's what the use of the technology, right? At least I could able to get this, which I have taught them in the previous semester, that is when they are in the 3rd semester, right? Okay, so as I said, what is tri-state buffer or three-state buffer, right? So you can see many a time the gate output only be connected to a limited number of other gate input without without degrading the performance of the digital system. That's what we have seen. It depends on the fan in and fan out. But sometime we need to connect the output of the gate, output of a particular gate, to some other inputs of the gates. In that case, it may happen that because of the limited fan out capability, that output of a particular gate may not be driving the inputs of the other gate. In that case, to boost the strength of that output signal, which can be used as an input for other, we need a device that is called as a buffer or a tri-state buffer or a three-state buffer. So buffer is like, I can say that a unity gain amplifier, you can say. You know that. What is amplifier? Of course, amplifier will not come in the digital part. It will come in the analog part. So can anybody tell me what do you mean by an amplifier? Yes?
Device which is used to increase the amplitude of the wave.
Not only amplitude, madam, the device which increases the strength of the input weak signal, you can call. Not necessarily only amplitude. It may be frequency also, or it may be amplitude, it may be phase, or it may be current, it may be voltage, it may be power, anything, right? So in general, we can say that a device which increases the strength of the input signal is called as an amplifier. So amplifier will have certain gain and it will increase the input by that particular factor. For example, suppose if you have an amplifier with gain 10, and if you have given an input of 1 volt, what output you can expect from that? Are you getting my question? You have an amplifier whose gain is 10, and you have given an input of 1 volt to that particular amplifier. So what output theoretically you should expect from that amplifier? Yes? What should be the output? Normally, output of an amplifier will be the gain times the input. That's why I said gain is a multiplication factor. By how much amount input should be increased or multiplied, that will be decided by that multiplication factor. Right? So in this case, what will be the output? Can anybody tell me what will be the output in this case?
10 volts.
Yes? How much?
10 volts.
10.
10
Yes,
volts.
exactly 10 volt. Because input we have given as how much? 1 volt. Since we have given input as 1 volt and the gain of that particular amplifier is 10, 10 into 1, we are going to get 10 volts as the output. That is the normal amplifier which we use for strengthening the input weak signal. Now, if you have an amplifier with gain 1, what will be the output that you are going to get? Assume that you have an amplifier whose gain is 1. We call it as unity gain amplifier, or sometimes it is also called as voltage follower or the buffer. If the gain of the amplifier is 1, what will be the output of that particular amplifier? Yes?
Same as the input.
Same as that of the input. Now the question arises, why such amplifiers or buffer or voltage followers are required? Because normally we use something to get something different than what we give. right? But here, whatever input you are giving, same you are going to get the output. Then why such amplifiers are required? Are you getting my question? Yes. Why such amplifiers are required then? Yes, Sahil? Because what Jyoti said is right. When the amplifier gain is 1 or unity, output follows the input. So whatever input you give, the same you are going to get it at the output, right? Then my question is, why such a unity gain amplifiers are required? Because there is no change. What you give, the same thing if you are getting, why that device is required? Yes, Sahil?
Maybe while processing, we can lose data.
Yes, any other answer? Akanksha? Yes, that's where these buffers come into picture. Like as I already given you the answer, I told when you are having a gate output and if that gate output you are connecting to other inputs of the gate, it may happen that the output of the gate may not able to drive the inputs of those other gates because of its insufficient strength, right? I need to get the same, but its sinking or sourcing current may be less. Hence, such buffers are required. Like the same thing happens in the unity gain amplifier. When the gain is 1, output will be equal to input, but it strengthens or it strengthens that signal in sense that its current handling capability can be increased, or it basically used for the other purposes like impedance matching and all. Most of the time there has to be a proper impedance matching. When impedance of source matches with the input impedance of the circuit, there will be maximum power transfer. Similarly, when the output impedance of the circuit matches with the load, the circuit will give you maximum output, right? Hence, in order to have the maximum power transfer, we go for the impedance matching, and to achieve such impedance matching, normally we go for the voltage followers or the unity gain amplifiers. Exactly in the same way, in digital electronics, we use similar to unity gain amplifier called buffers. Don't get confused. Don't call these buffers like amplifier or unity gain amplifier. These are totally different in the digital electronics. So we can use a simple buffer to increase the driving capability of the gate. And to increase this driving capability of the gate, we use the tri-state buffer so that we can connect the output of one gate to the inputs of the many other gates without deteriorating the output of the previous gate and without changing the input levels of the succeeding gates to which we are connecting these inputs. So I hope, what do you mean by tri-state buffer? We are going to discuss in detail. I hope all of you understood what is buffer. All of you understood what is buffer here? For a time being, forget about that amplifier part, which I have explained to you. Just to give the analogy, I have given that example of an amplifier. Don't relate now exactly with this amplifier. The buffer, as I said, it is basically is used to increase the driving capability of the gate. That means the sourcing or the sinking current should be maintained so that the function of the gates should not be deteriorating. They should not, there is no deviation from the actual behavior of the gates. For that, in between, we add these buffers so that we can connect the output of one gate to the input of the other gates without changing the output. So here I have shown, I think all of you can see this. Right, I think there is some problem. I'll do it once again. Where is that? 280 notes. Yes. Okay. This is what we are discussing, and is okay, fine. Now you can see here the symbol for the tri-state buffer. Normal buffer will be like your NOT gate without bubble. If you have a NOT gate without bubble, that is called as a normal buffer. In normal buffer, what happens? Always output will be equal to input. In normal buffer, what we give is, say, like A will be the input and C is the output. This additional B signal will not be there in the normal buffer. But we are discussing here what? A tri-state buffer. So in tri-state buffer, we'll have one more control signal like B here. So how exactly this tri-state buffer functions? Right? So whenever B is active, C will be equal to A, and when B is not active, C will be connected to high impedance. That's why it is called as tri-state. What do you mean by tri-state? Three different states, either high or low depending on the input, and there is one more third state that is called as a high impedance state or the open state. That's why this circuit is called as a tri-state buffer. And the third state is called as high impedance. So it is exactly similar to this switch. You can see here in this switch what happens when the B is closed. When the switch B is closed, C will be equal to A. And if switch B is open, what will be the value of C? Yes?
High.
Are you getting it? What happens when when B is open? C is not connected to input. It is disconnected from the input. It is left open. So that state of the output is called as high impedance state. Hence, this particular buffer is called as tri-state buffer. I hope it is clear what exactly you mean by tri-state buffer. Is that clear? All of you understood? The symbol is this. Based on B, if B is 1, C will be equal to A, and if B is 0, C is not connected to the input, it will be at high impedance state. So there are 4 different types of tri-state buffer you can see here. One is normal buffer, which are shown there, which is called as active high buffer. So in active high buffer, you can see here when B is 0, irrespective of A may be either 0 or 1, what will be the output C? When B is 0, high impedance, and that is denoted by letter Z. Don't say that Z is some different output. Z is nothing but the high impedance state. So when B is 0, irrespective of A, C is always high impedance. But when B is 1, what is C? When B is 1, C will be equal to A. So if A is 0, C is 0. If A is 1, C is 1. That means you can see here the output C can take how many different values?
3 different values.
Three different values. That is either high, low, or high impedance. That's why this buffer is called as what? What it is called as?
Tri-state buffer.
Tri-state buffer, because it is having 3 different states. So this is first kind of tri-state buffer, active high buffer. Then can you tell me what is this? What is the difference between the first and the second arrangement here? The second one is called as what? Active low buffer, right? Or inverted buffer. You can call it as active low buffer or the inverted buffer with active high enable, right? So again, you can see here in this case also, when B is 0, irrespective of A, what is C?
High impedance.
High impedance. But when B is 1, what is C here? You can see
Complement of A.
complement of A. Why complement of A you are getting? That is because of what? This
Inverted buffer.
bubble. Because of that bubble, you get the output inverted. So that is the second kind of tri-state buffer. You can see when B is 1 and A is 0, you are getting C is equal to 1. And when A is 1, you are getting C equal to 0. That is the second type of buffer you have. Now, can you tell me what is this third type of buffer? What is the difference between this and the previous buffer, the first one or the second one we have discussed? Yes? The third buffer is what? It is again active high buffer, but with what?
Low enable.
Active low enable, right? So this particular buffer will be active only when B is, yes,
0.
this is active only when B is 0. It is reverse, opposite to the previous two which we have seen. Previous two buffers were active when B is 1. But here, the next two which we are discussing, those will be active when B is 0 because of this bubble. Whenever a bubble is added, it is like a negative logic. That's what you should remember. So when B is 0, you can see here, whatever value A takes, the same you are going to get. And when B is 1, what happens?
High impedance.
B is 1, the output C will be in high impedance state. Right? Similarly, what is this fourth one now? It is similar to this, but with one change. What is that? Here there is no
Active low
bubble,
enabled.
right? Here we have a bubble also. So it is active low enable, and the output is inverted. Output will be inverted. You can see when B is 0, then it is active, and when A is 0, when B is 0 and A is 0, C you are going to get the inverted of A, that is C is equal to 1, and when A is 1 you are getting 0, and when the enable, that is B is 1, it is not active, you will get the output as high impedance state. Is that clear? The four different types of tri-state buffers. Is it fine?
Yes, sir.
Now, can you implement 2:1 mux using these tri-state buffers? Because if you see here, this normal buffer, I said C is equal to A when B is equal to 1, and C is high impedance when B is 0. But what is our 2:1 mux we have? In 2:1 mux, we'll have a select line, and when that select line is 0, it should select one of the two inputs, and when that select line is 1, it should select the other input. That is what is 2:1 mux is. Right? So how to construct such 2:1 mux? You can see here now. 2:1 mux is this, which has two inputs, one select line and one output. So I have shown B as the select line, A and C as the input, and D is the output. So how it can be constructed using the tri-state buffers which we have discussed just now. So we are using, what is this tri-state buffer we are used here? This is active high tri-state buffer, and this is also active high tri-state buffer with what? With active low enable, right? So how this particular circuit works? Can anybody explain me how this circuit works? Yes? Can anybody give? It is like you should get the functionality of 2:1 mux. So how you can explain the operation of this particular circuit? You have to explain what happens when B is 0, B is 1. That's all. Because that is the control line or select line that we are using here in this 2:1 mux. So what happens when B is 0? Which tri-state buffer will be active and which is not active? So what output will be finally connected to the output terminal? Yes? Yes, Swapnil? Can you explain? Swapnil, are you there?
Yes, sir.
Yes, can you give a try? What happens when B is 0, B 1? That's what you have to explain here, nothing else. Yes? Just give a try. Check what happens when B is 0. There are two tri-state buffers now. Which will be active, which will be inactive, and what will be the output D. That's what you have to tell.
When
Yes.
B is 0,
B 0.
A is active.
Yes.
A-
I'm asking
A
to
is
Swapnil, Jyoti. Let him finish first. Swapnil,
Sir, B will be
yes.
active.
When B is 0, what
0.
happens? You tell me. Which tri-state buffer will be active out of the two? You can mark upper one as tri-state buffer 1, the lower one as tri-state buffer 2. With D equal to 0, which buffer will be active and which will be inactive? Yes? That means you have not understood what is tri-state buffer, right? Yeah, anybody else?
So when B is 0, A will be active. I mean, buffer 1 will be active.
Buffer 1 will be active, buffer 2 will be inactive. So
Inactive.
output of buffer 1 will be what?
D is equals to A.
Output of buffer 1 is A. And what
A.
will be the output of buffer 2?
C.
How C, man?
Uh,
When B is 0, I am asking for B equal to 0 case. When this B is 0, this buffer will be active and this will be inactive. That means here we get A and here we get what? High impedance, that is Z. When the buffer is inactive, what will be the output? Yes?
High impedance.
Z, high impedance. That means for B equal to 0, here we have got A and here we have got Z. Z means it is open, it is not connected. So obviously this A will come to the output. Is that clear?
yes.
This A will come to the output D. Similarly, when B is 1, if you take B1, this will be active, this will be inactive. So since this is inactive, here we get what? Z, and here we get C. Z means open, this is not connected, and this C, what we are having, will come to the D. So when B is 0, A is coming to the output, and when B is 1, C is coming to the output. Hence this particular arrangement of two tri-state buffers connected together act like what? 2:1 multiplexer. Hope it is clear? Yes. So the same thing is shown here, circuit with two tri-state buffers now. What will happen? Right, because here two tri-state buffers output we have connected, no? There may be conflict sometimes. So how that conflict is resolved? That is shown here. Say I have shown here two buffer. Here A is input, B is control line or the enable, C is input, D is control line, and the outputs are, output of first buffer is S1, output of second buffer is S2. So when it may happen that sometime you get this as 0 or 1 or Z. S1 can take three values. What are the three values X can take, S1 can take? 0, 1, Z. Here also it can take 0, 1, Z, and we may assume one more don't care value also. So if you take those four values 0, 1, X, Z, 0, 1, X, Z, if S1 is 0 and S2 is also 0, then what will be the value of this F? Like means when D is 0, D is 0, obviously we are going to get S1 is 0 and S2 is 0 if we get, depending on the values of A and C. In that case, what should be the final value of F? Right? So 0 and 0, it gives you 0. Is that clear? Because both are 0, so this will be 0. But now, suppose if S1 is 1 and S2 is 0, what value F should assume? Like this fellow will ask F to take his value, that is 1, and this person will ask to take this value 0. Then F will take which value? Yes? When S1 is 1 and S2 is 0, what value F will take? Yes? F will be what? Don't care in that case. Like unknown value. It will take unknown value. We don't know whether it will assume 0 or 1. Because you are asking to take two different values simultaneously. Is it possible to accept two different values for a particular signal? No. So in that case, the output will be what? Unknown, X. Don't care what we call. Similarly, if it is 1 and 1, definitely we'll get what? 1. If it is 1 and 1, we'll get 1. Similarly, 1 and don't care or 1 and unknown will be unknown. And if we have 1 and Z, in this case, what we will get? Because that's what I have told in this case. When we have 1 and Z, Z means it is high impedance. It is like open. In that case, 1 will dominate there. So the output will be what? 1.
1.
Right? Similarly, if you have 0 and Z, in that case also you are going to get what?
0.
0. That means wherever Z is there, Z means it is like an open circuit, high impedance state. So other value it will take, that is either 0 or 1. And if you have X and X, obviously it is X. X and anything will be X only. And Z and 0 is 0, Z and 1 is 1. Z and X is X, we don't know. And Z and Z will be Z. These are the different values that tri-state buffer with two different buffers, like if connected to a common point, what value that output assumes is shown here. Now one example is shown here. Draw the block diagram for a 4-bit adder with the 4 sources for one operand using tri-state buffer. Right. Normally 4-bit adder means what? It should have A and B as 2 4-bit signal. There should be one carry in and some 4-bit output and the carry output. This should be the normal block diagram of a 4-bit adder. 2 4-bit inputs along with input carry, and it will give 4-bit sum and the carry. This, if you want to implement using what? The tri-state buffer, it can be done like this. One input can be given directly to the 4-bit adder, and the other input can be connected to a common line which is called as a bus. A common bus can be used, and to this common bus we can give the enable signal as well as the the inputs, the other 4 inputs, and accordingly we can get the output. So that is about the tri-state buffer. Many a time they may ask, write short notes on tri-state buffer or explain different types of tri-state buffer. So you should know what is buffer, what is the difference between buffer and tri-state buffer, what are the 4 kinds of tri-state buffer, and how those buffers can be used in digital electronics or the digital circuits. I hope it is clear. All of you understood? Yes?
Yes, sir. Yes, sir.
Yes, sir.
All of you understood what is tri-state buffer? Right. Now next, we have to go for the last part of this particular module, that is ROM, PLA and PAL. Right. So anyhow, I need not explain much about this. You have already studied different types of memories, I hope, in your computer organization course. Have you studied memory, different types of memory, memory management, everything? So on?
Yes, sir.
Have you studied different memories in computer organization subject?
Yes, sir.
Yes. So can you tell me what is ROM then? If you already studied, it is just a repetition for you people. What do you mean by a ROM? ROM stands for what?
Read-only memory.
Read-only memory. So what exactly you mean by read-only memory? What it consists of? Anyhow, the answer is there in the screen. I hope it is visible for all of you, though it is scanned one. Can you read that? What is written there, Sohan?
Yes, sir. A ROM consists of array of semiconductor devices that are interconnected to store binary data. Once the data is stored in the ROM, it can be read at any time, but the stored data cannot be changed under normal operational condition. There are 3 types of ROM, that is mask programmable ROM, electrically erasable ROM, TROM.
Electrically erasable ROM. So I hope all of you have understood this. What is ROM? Basically, it is array of semiconductors or array of different transistors connected together to store some binary information into it. And one important property of the ROM, unlike the other memory devices, is that once the data is stored in the ROM, it can be read any number of times. Whenever you want, you can read it. But only once we can store the data into the ROM under normal operating condition, I am telling. So it is not, you should not take it for granted that once the data is stored in the ROM, we cannot change it. Yes, under normal operating condition, it is not possible to change. But now there are various ways by which we can change the data stored in the ROM also. Right? That's what you should keep it in the mind. Or else you should not say that sir has told under any condition, once the data is stored in the ROM cannot be changed. No, under normal condition, it is not possible to change. But by using special means, definitely the data stored in the ROM can be changed. And there are 3 different types of ROM which I have mentioned here, which you will be studying. right? Of course, now there are many other types of memories are also available. So here in brief, we'll be discussing about MROM, that is mask programmable ROM, then PROM, programmable ROM, and then EEPROM, electrically erasable programmable read-only memory. Here, in fact, I'm making a contradictory statement, right? There I said under normal condition, you cannot change, but here at the same time, I am telling you people that we have electrically erasable PROM. So what could be this electrically erasable programmable read-only memory? Yes? Electrically, by applying voltage, by applying electrical means, you can erase the data already stored and you can reprogram. That is what is the meaning of this. That is electrically erasable, programmable, read-only memory. Fine. So we have various forms of the ROM. The general structure of a ROM is shown here. Like it can have n input lines, which we have shown here. Then each can have we can have 2 to the power into m ROM. When I say it can have 2 to the power n memory locations, and each memory location can store m words. Say for example, if I say if I take say n is equal to 4 and m equal to 8. Can you tell me what is the meaning of this? I'm telling n equal to 4 and m equal to 8. So what exactly this memory looks like, or what is the composition of this ROM when n is 4 and m is 8? Yes? When I say n 4, 2 to the power n is how much?
16.
16, and m is 8.
8.
That means that memory will have how many memory locations?
128.
No, how many memory locations?
Memory.
16 memory locations, and each memory location can store how many bits of information? 8 bits of information. So 16 into 8 is how much?
128.
128 bits of information it can store. But there are how many locations? Only 16 locations.
16.
And to select one among these 16 locations, how many address lines you should have? There are 16 memory locations, right? So if you want to access any one among these 16 memory locations, you need to send an address. So how many bit address you need? Yes? That's what these input lines, what you have shown, are nothing but the address line. These input lines are not used to store the data into the ROM. These are used for what? Sending the address, right? Say for example, if you have a memory of 1 kilobyte, 1 kilobyte means how many bytes?
1024.
1024 bytes. So to access 1 kilobyte of memory, what should be the address bus size? Are you getting my question? You have a memory of 1 kilobyte. So 1 kilobyte memory means what? It can have 1024 locations. And each location, I'll assume again that of 8 bits. Because normally 8 bit is called as a byte. And memory will be byte oriented. So I have 128 kilobytes of memory. Right? When I have 1 kilobytes of memory, how many address lines you need to access a particular memory location?
128.
128? No. I'll give you a simple example. Suppose you have a memory of only 8 bytes. Right? You have a memory of 8 bytes. Means what? There are 8 locations, and each location can store how many bit of information? 8 bit of information. So if you want to access one among these 8 memory locations, how many address lines you require? How many address lines?
3.
Or what is the size of the bus? 3, exactly. Because 2 to the power 3 equal to 8.
8.
Like that. If you have 16 bytes of memory, how many memory address lines you need?
4.
4. Huh? Then if you have say 1 kilobyte now, how many memory locations are required?
10.
Just a minute, just a minute. There is an interruption. Sorry. Okay. So, hello. Sorry for the interruption. If you have 1 kilobytes of memory, now how many address lines you need?
10.
Yes,
10.
exactly 10. 2 to the power 10 is 1024. So you need 10 address lines. Like that, if you have 64 kilobytes of memory, then you need 16 address lines. If you have 1 megabyte of memory, you need 20 address lines, and so on. So what happens is, if you go on increasing the memory size, the address lines required will go on. Right. So as you go on increasing the memory size, number of bits required in the address bus goes on increasing. That's why normally when you buy any system, let it be laptop, desktop, or including your hope now you understood why there is a restriction on the internal memory. Why can't they increase the memory size to the larger extent, right? Of course, now memory is available at throwaway prices. You can increase the memory size like anything, but if you go on increasing the memory size, what you need to do is at the same time, you need to increase the number of address lines required, and hence there is a restriction on the what? How much amount of memory to be used in the system, let it be desktop, laptop, or smartphone, etc. So how exactly this ROM can be used to implement different functions? That's what we are going to study. We have seen multiplexer, decoder, encoder, how they can be used to implement different functions. Now we are going to study how ROM, then PLA and PLA can be used to implement the different function, right? So we'll stop here for the day. In the next class, we'll try to study the implementation, ROM implementation, as well as PLA and PAL implementation.